Hello everybody and welcome back to Advanced Maths. Today we're going to learn some trigonometric identities and how to use them. Let's start by refreshing Pythagoras' theorem. A squared plus b squared equals c squared, and we're going to try and build upon this. Well, we can divide by c squared and we get a squared divided by c squared plus b squared over c squared is equal to 1. But now we can think of trigonometry, SOHCAHTOA. And if you've got an angle labelled theta, the opposite here would be A, the B will be adjacent, and the C will be the hypotenuse. So therefore, A divided by C is the same as opposite divided by hypotenuse. And B divided by C is the same as adjacent divided by hypotenuse. This means A over C can be replaced by sine of theta, and B over C can be replaced by cos of theta. Let's do that. And we get this. Sine theta squared plus cos theta squared is equal to 1. That is a really famous identity, and it is always true in mathematics, no matter what theta is. We normally write it like this though. Sine squared theta plus cos squared theta is equal to 1. And sine squared theta here means you take the sine of an angle and then you square the answer. So sine squared theta is like that. And it doesn't matter what the angle is, any number that goes into this will always work. For example, sine squared of 60 plus cos squared of 60 will be 1. We can rewrite this like this, take the cos squared theta off both sides, and we get the expression for sine squared theta, or we could also write it like this, which gives us an expression for cos squared theta. That is the Pythagorean identity, and it is very, very important in mathematics. Now we've got another one to show you. We've got sine theta is op over hype, cos is adj over hype, and tan is op over adj. And we're interested to know what sine theta divided by cos theta is. Well, this is op over hype divided by adj over hype. And if we keep change flip here, that's how we divide fractions, we get this. And the hype cancel. We've got op over adj, which is the same as tan. And so we've shown that sine of theta divided by cos of theta is always equal to tan. And that's again a really famous equation in mathematics. It's an identity in mathematics which is always true no matter what theta is. Finally, we've got our double angle identities. I'm not going to show you the proof of these. You are welcome to look these up yourself, but they are always true. No matter what theta is, these are always true. And they're very useful for when you've got a 2 theta or a 2x inside of a sine or a cos. If ever you see sine 2 of x or sine 2 theta, you are probably going to be using your double angle identities. So, those are all identities we've learned today. Now let's put them into practice. Here we've got an example, and it says, given that sine of x is 4/5, find cos of x, find tan of x, find cos of 2x, and find tan of 2x. Okay, let's start with A. We're going to find cos of x. And here we need to choose an identity that links sine of x, which we know already, to cos of x. And I think we're going to use the sine squared theta plus cos squared theta is equal to 1, the Pythagorean identity. Because, as I say, this links sine of x to cos of x. So let's copy down our identity, and now we can rearrange. We can take sine squared theta to the other side, and we've got cos squared theta is equal to 1 minus sine squared theta. And now we can square root. And that gives us an equation for cos of x. And all we do now is put sine of x is 4/5 into this expression. Like this. 4/5 squared is sine squared of x. And we can work this out on pen and paper. This is very easy. It looks confusing, but watch my steps. 4/5 squared is 16/25, and 1 is the same as 25/25. 25/25 is the same as 1, so I'm just writing it with a common denominator here. We subtract the top, 25 minus 16 is 9/25, and we square root everything. We get 3/5. Square root of 9 is 3, square root of 25 is 5. Cos of x is 3/5, and we are finished. Now let's do tan of x. And tan of x, we're definitely going to use a sine of x over cos of x equation, because that is how we find tan of x from sine and cos. So tan of x is sine of x over cos of x, and we're going to substitute sine of x is 4/5 and cos of x is 3/5 in here. So sine of x divided by cos of x is 4/5 divided by 3/5. I'm going to keep, change, flip. We get this, the 5 and the 5 cancel, and we've got tan of x is 4/3. And that is the answer. Now let's do cos of 2x, and here we are going to use our double angle identities. So I can pretty much use any of the cos double angle identities. There are 3 separate ones which all work. But cos 2 of x, I'm just going to use 2 cos squared of x minus 1. And I'm going to substitute cos of x is 3/5 into here, so it's 2 times 3/5 squared minus 1. 2 of 3/5 squared minus 1. I square everything in the bracket, I get 9/25, and I get 18/25 because I times everything by 2, minus 1. And 1 is the same as 25/25. So you can do 18/25 minus 25/25, which is minus 7/25. I'm just subtracting the top. 18 minus 25 is minus 7. And so cos 2 of x is minus 7/25. Very good. Finally, let's work out tan 2 of x. And here I'm going to use 2 separate identities. I'm going to first use sine 2 of x is equal to 2 sine of x cos of x, and then I will use tan of x is sine of x over cos of x. So sine 2x is 2 sine x cos x. I'm going to use this because the question is about double angles. It's tan 2 of x, so I think sine 2 of x is going to be useful. And sine of x is the same as 4/5, cos of x is the same as 3/5, so I substitute them in. And I work this out. I multiply everything, I get 24/25. Next I can do tan of x is equal to sine of x over cos of x, and that means that tan 2x is the same as sine 2x over cos 2x. And so I can do sine 2x divided by cos 2x and substitute those in. I know sine 2x is 24/25, and cos 2x I've already worked out was minus 7/25. Keep, change, flip again, and the 25 and 25 cancel. Tan 2x is equal to minus 24/7, and that's the final answer. And there we have it. We have used our trigonometric identities to solve some problems. Okay, you will also use this in more complicated equations, and you'll probably use this with cast diagrams in your exams. You might want to check out my video about cast diagrams while you're here. Thank you for watching this week's video from Advanced Maths. Remember to like and subscribe so you don't miss any future videos. We're covering GCSE, A-Level and IB Maths with quick and simple explanations, and new videos are coming very soon. You can also check out advancedmaths.com for more free revision resources. Thank you for watching, and good luck in your exams.